In this video, we're going to be doing some problems related to stoichiometry and gases that are not at STP. Here's an example problem. It reads, if 3.25 grams of baking soda is added to excess vinegar at 27 degrees Celsius and 0.98 atmospheres, what volume of CO2 gas is produced? Since this is not at STP, we cannot use the 22.4 liter shortcut. So instead, we have to work this out by hand. Let's start by writing a balanced chemical equation for this process. So we have baking soda added to acetic acid. And that's going to produce sodium acetate. Yeah, write a 3 there, that's a 2. And then we're going to form water and carbon dioxide gas as products. All the coefficients here are 1. So we can go ahead and get started. We are going from baking soda to carbon dioxide gas. So I'll start over here. We have 3.25 grams of baking soda. I'm going to need to get that from grams to moles of baking soda. So that's going to be my molar mass. And so that's going to be 1 sodium plus 1 hydrogen plus 1 carbon plus 3 oxygens. And so that's 84.006. And go ahead and store that in my calculator as A. Now I can cancel out my moles of baking soda and get into moles of carbon dioxide. I'm going to stop there because now that I'm in moles, I can plug in moles into my equation for gases because PV is equal to nRT. So moles is my N value. So I can type this into my calculator, 3.25 divided by alpha A times 1 divided by 1. Not that that's going to do anything, but that is 0.0386877 . Now store that as alpha B, so I don't have to retype it. And so now I'm going to be solving for volume. Since this is not at STP, I have to use the PV is equal to nRT equation. Solving for V, PV equals nRT, I'll end up with nRT over P. This is my N value. So that is 0.03868, blah, blah, blah. I'm going to go ahead and my pressures in atmospheres, so I'm going to use this liter atmospheres per mole Kelvin value for R. My temperature needs to be in Kelvin, so 27 plus 273.15 is 300.15. And then my pressure is 0.98 atmospheres. And so this is going to be need to get my moles times 0.08258 times my temperature divided by my pressure. And that is 0.9723. My pressure only had 2 sig figs, so I'm going to report my answer to only two significant figures, and so that is 0.97 liters. So the volume of this balloon would be approximately 1 liter given this mass of baking soda. Here's another practice problem for you. This one reads, baking soda breaks down into sodium carbonate, water, and carbon dioxide gas when heated. If a recipe calls for 1 teaspoon of baking soda, what volume of carbon dioxide will be produced in the oven at 1 atmosphere and 375 degrees Fahrenheit? Go ahead and pause the video and work this out on your own. And then unpause the video when you're ready to continue. The balanced equation is provided to you here. Okay, that equation wasn't quite balanced. It was missing the 2 coefficient. Now it's balanced. All right, let's go over this. So first we're going to have to figure out how many moles of baking soda that is. And so that means we're going to try and find moles, or we have to given moles. We're not quite given moles, but we're going to go for moles of that. Got to get into moles somehow. Then we can switch to moles of CO2. And then we'll find volume of CO2. But we have to figure out how to get into moles. We can go from teaspoons to milliliters, and then use the density to get into grams, and then out into moles using the molar mass. So let's go ahead and do that. I have 1.0 teaspoon of baking soda. To save room, I'm not going to write baking soda. Then I'm going to use this metric to English conversion to get into milliliters. Then 1 milliliter is 1 centimeter cubed. And then from the density, I know that 1 centimeter cubed would have a mass of 2.2 grams. Now I can use the molar mass in order to convert my grams into moles of baking soda. And before, in the previous practice problem, I saved its molar mass as A. So that is the molar mass. That has a 2 coefficient. And then there's a 1 coefficient for the carbon dioxide gas. And then we're going to stop there because that's going to give us our N for PV is equal to nRT. So we have 1 times 4.93 times 2.2 divided by 84.006 divided by 2. And that is 0.6064. So I'm going to go ahead and store that number as A. So now that's stored in my calculator as A. I'm going to just make a note to myself that that was A while I continue. And so now I can plug in that to my PV is equal to nRT equation, solving for my volume. I'm going to need to get this into Kelvin. Some graphing calculators and, well, some scientific calculators have a built-in conversion function. And so you can convert from Fahrenheit into Celsius and then do the conversion from there into Kelvin. So that is 463 Kelvin. I'm going to go ahead and store that in my calculator as B. So now I can type this all into my calculator because I got my moles. My pressure's already in atmospheres, that's good. And so I can grab my R for atmospheres, my Kelvin temperature, divide that by my pressure, which is 1.00 atmospheres, and what do I get? Rather than retype my N and my temperature, I'm going to recall those numbers from my calculator. And so that is 2.456 liters. And let's see, how many sig figs? That's 2 sig figs. So I'm going to end up with 2 sig figs. And so that's going to be 2.4 liters. Here's another practice problem for you. It says, what volume of carbon dioxide gas is produced when a 280 milliliter bubble of ethine is combusted at 0.951 atmospheres and 25 degrees Celsius? Go ahead and pause the video and work this out. Okay, so let's go. All right, there's a long way and a short way. The long way would be to use PV is equal nRT in order to solve for N of the C2H2 gas. Then once you have moles of that, then you use the molar ratio to switch compounds. And then you use PV is equal nRT to get back out into volume of CO2. But you could also do this a shorter way. And that's the way I'm going to show you, because I think that most likely you went down this rabbit hole. Remember that law of combining volumes? That did not have anything to do with STP, so we can still apply that since our initial bubble is given to us as a volume, and we are not given different temperatures or anything, so we can assume that this was recorded at the same temperature and pressure as before. So that means that we can take our 280 milliliter bubble of C2H2 and just apply this ratio to cancel out our C2H2 and get into liters of CO2. So that's going to tell me that I'm going to have essentially twice as much CO2. And you can see here that the liters cancels out, and then I'm left with milliliters of CO2.